All right, but multiplying polynomials is a really interesting topic, and I kind of have a story to go along with it. And this is a true story from when I was in college. When I was in college, one of my professors put this problem on the board, and he said 23 times 17, and we all, no problem, that's a piece of cake, and we all did something like this. We all said, okay, 23 times 17. This is how we were taught in elementary school. Okay, 7 times 3 is 21. So we put the 1 here, put the 2 there. 7 times 2 is 14, plus 2 is 16. Make sure you put a 0 down here. And 1 times 3 is 3. 1 times 2 is 2. Add it all up, and we have 193. The answer is 391. And that's great. That works. There's nothing wrong with that. But this person, he really challenged us to think why is that true? And the main ones were like, why do you put this 2 here? Why do you put this 0 here? What's going on in that problem? And if you really understand multiplication, it's very simple. But many people couldn't explain it. So what he challenged us to do is to think about it in terms of this. And this is another way I'm going to show you. It's really the same type of multiplication, except we're gonna ask ourselves slightly different questions. So 7 times 3, that's still 21. I'm going to write down 21. But this is not 7 times 3. This is, or 7 times 2. That's 7, but times a 20. And 7 times 20 is 140. Okay, which starts to show why that value should be 161. 21 and 140 is 161. So you're getting the same numbers, you're just making sense of where they're coming from. And we can keep going. Again, we have to ask ourselves not what is 1 times 3, but this is a 10 times a 3, which is 30. And this isn't 1 times 2, it's 10 times 20, which is 200. And now, again, we start to see where that 230 is really coming from. We see why this 0 is here, and then we can just add all those things up. Either way, we're going to get 391. Okay. Now, I'm not doing this to show you to get you to stop doing this. I just want to make sure that we can take advantage of the blue one to actually help us multiply. And this is another, yet third way to multiply. And many people, when they're learning this, don't like it, but today we're really going to see the value of learning this style. So we're going to represent 20 as 20 plus 3, and we're going to represent 17 as 10 plus 7. And it's the same exact computation, same calculations, we're just organizing it in a slightly different way, and we can start to see that 20 times 10 is 200, 10 times 3 is 30, 7 times 20 is 140, and 7 times 3 is 21. We're getting the exact same numbers we did here, so naturally when we start adding up these things, we should get the same exact value, 391. Again, not trying to get you to stop doing the red. I'm just saying don't understand why. Because if you understand why, even with something even bigger, we can really do more things, which is, I like when you can use one tool to do lots of things rather than one tool for one problem, another tool for another problem, is what I think some people struggle with math sometimes. So can we explain what's going on? Of course we can. The 300 is just she's using units to hold a place value, and 40 is holding that place value, and 2 is holding that place value, so that we can start to see the product that's being formed when we start to multiply numbers. Again, and then here's our 20 and here's our 3, so we can add those like units. Here's my thousands units, my hundreds units. I have a 10 and a 100, which all these things can be combined. I'm just combining units to come up with a final solution, and her final answer is just going to be the sum of all of those values. So just add those up and we're good. When numbers are in, it's really easy to see. But here's the beauty of what we just did. Take away hundreds, tens, and ones and replace it with x squared units, x units, and constants. X units and constants, it's the same problem, which is really cool. So if we set that same strategy up, one strategy even though there's variables, here is my x squared unit holder, my x unit holder, my constant unit holder, my x unit holder, and my constant. So this visual represents 3x squared plus 4x plus 2 times 2x plus 3, and we just multiply. So 3x squared times 2x is 6x, and x squared times x is x to the third, one more power of x. 4x times 2x is 8x. 2 times 2x is 4x. Sorry, I apologize. 4x times 2x is 2x, or sorry, 8x squared. 4 times 2, 8x times x, x squared. 3x squared times 3 is 9x squared. 4x times 3 is 12x. And 2 times 3 is 6. And just like we did with numbers, with thousands, hundreds, tens, and ones, now we just have like placeholders. We have like units. So I have my 6x cubed term. That's my only cubed term in this whole model. Then these two are like terms. These two are like units. So I have 17x squared. And these two are like units, which means I have 16x. And then my constant by itself is 6. And to the untrained eye, these seem like different problems, but if you start to see similarities, we start to see units. We have 6, 17, 16, 6, 6, 17, 16, and 6. We start to have like units. It's the same problem.